Time now to introduce Dr. John T.C. Lee, the President and CEO of MKS Instruments. MKS enables technologies that transform our world. They provide technology solutions for leading-edge semiconductor manufacturing, electronics and packaging, as well as specialty industrial applications. MKS is a global leader with revenue of $3.6 billion and over 10,000 employees. John has been with MKS for 15 years and played crucial roles in expanding the global presence of the company, driving substantial growth in photonics, semiconductor and chemistry applications.
Thank you. It's a great honor to be here. Thanks to Optica for organizing and inviting MKS to give this opportunity to talk a little about MKS, as well as how we use photonics. So if you want me back, Jose, there's this nice boat in the harbor there. I heard Darren looked it up and said somebody owns it, like a Russian oligarch. He might be able to sell it for a lot cheaper. So you get that, I'm back, okay? I want to take a slightly different spin on the use of photonics. We have been a semiconductor company now moving into photonics. But what I'm going to be focused on a little bit is setting the stage for how semiconductors have evolved and the new challenge for advancing more than Moore's Law and how photonics plays in that. And so photonics solutions enabling advanced packaging in the AI era. If you saw me on the panel, I was already talking about how packaging is quite important. Semiconductors are hard to do, necessary, but no longer sufficient. We need packaging. So that's going to be the focus, and I'm going to talk a little bit about how photonics is enabling that today. So this slide many of you might have seen, but on the x-axis, of course, is time, and then on the y-axis is the amount of data generated by mankind in those years. And there's this line in the middle, and the nice little green bar you can barely see on the bottom, that's the data generated by human beings, you and I, right? And there's a crossover point in 2018 where the amount of data generated by us is now smaller than the amount of data generated by everything we've invented, like machines, okay? And so this is just to tell you that in the not too distant future, the amount of data being generated continues to grow exponentially, and you need a lot of semiconductors for that. And then this is a chart that you've seen different versions of. It's Moore's Law. Time again on the x-axis. Vertically is a log scale. And a couple of things to point out. If you look at the curve that's labeled frequency per chip, you see that it's a nice up and to the right curve during stage one, the Dennard scaling. So that's when we shrunk transistors and we got the benefit of going faster. Frequency kept moving with it, right? Without any kind of loss. And then it started flattening out. And it flattened out because the transistors started seeing each other and you couldn't really shut them off. And so that was, for those techies, that's leakage current. So you didn't get the frequency benefit as you put more transistors together and made them smaller. So what did people do? You see another line, number of cores on a chip. Well, let's divide the work up. So in one die, we could break up and make 4 CPUs or 8 CPUs or a GPU. You saw earlier talked by Luke, hundreds of GPU cores. And you divide up the work. Now you need software to use that efficiently, right? But for a while, it extended Moore's Law a little bit more. And this is the stage 2, the multi-core era. And that lasted for another 10 years, 15 years. And then it started asymptoting. And so what do we do now? This is the third stage, heterogeneous integration. And this is about putting multiple chips together, not on one die anymore, right? But multiple dies or chips on top of each other, and then connecting them. And because we are doing that now, we actually can extend Moore's Law. And of course, it's a party that we don't want to stop because this party allows things like AI. And that's why I say we still have to continue making chips more dense, smaller, because even though it looks like the frequency of the chip is asymptoting, it's still increasing. It just looks flat on a log scale. Same with cores. So you need that packaging to get that log scale benefit. So what about packaging? That market looks like this. The PCB market, if you will, is rather large, and this is a third of it. This is what we call the advanced packaging part of it. And the part that we're really interested in is that dark green part. And you can see that is the 2.5 or 3D packaging. That's the really complex, multiple chips on top of each other, multiple chips together, layers and layers and layers. I'll show you some pictures. That's growing at 20% CAGR. Just the advanced packaging part is growing at 10%. Regular PCBs are kind of growing at GDP plus, and a little bit more for phones, right? And so this is the exciting part and the necessary part for us to continue more than Moore's Law. So here's a picture, and it's quite complex. So at the top, you can barely see it, but on the right, it's a bunch of memory chips stacked on top of each other. This is HBM. Then on the left, you see a logic chip, and then you got to fill the thing so it looks like one big block. And then something in between the wafer level packaging and then the package substrate is RDLs, redistribution layers, that are made out of silicon or not so much silicon now, a mixture of silicon and polymers. But that is all done kind of in fabs, like TSMC packaging fabs. And then the package substrate, that's where you're putting very dense layers together. So you can see that's in proportion. There's a core layer with big holes in it, and you got to fill it with copper. And then on both sides are different layers of interconnects. These are usually polymers with glass fibers embedded in them. And we've got to take that material and we've got to drill holes in it, we've got to clean it, we've got to put copper in it, and then we've got to make lines and spaces of copper on top of it. And that's one layer, yeah? And then we've got to do it over again, and over again, and over again. And today, these package substrates would have that core layer. Usually, maybe 10 years ago, it was 5 layers on both sides. Now it's 10, going to 20 on each side. So think 25, 40 layers now. And that's the advanced packaging part. That's the hard part. And then you got these solder bumps, and you see another board beneath. And that is just a regular PCB, regular. That would be something where it's 4 or 5 layers, and you would say, that's my washing machine, automotive, and that is true. But for advanced packaging, because it's so dense, the number of chips at the top, it is now 30, 40 layers, okay? Older technology, but that's also growing as well. So you got to do all of this just to make, one GPU NVIDIA board work. And that is why I say the chip is necessary, but wow, look at that packaging. And so when you think about where the technical challenges are coming for the industry to keep more than Moore's Law going, well, you got the semiconductors thing. A lot of folks have talked about how hard that is, and it is hard. I think Luc Van Hoven said the ASML extreme ultraviolet lithography tool is $250 million to $300 million. If you want the better one, it's $400 to $500 million a copy, right? That's really hard to do. But look at all the work that we think we will need for advanced packaging. More layers, smaller features on each layer, and Moore's Law is about making things cheap. If the industry can find the cheapest way to do it, you get to have this party continue. And we see all these technical challenges in packaging, and we see the same kind of movie that we saw in semi, it's just 30 years later. So semi 30 years ago looked hard then to everybody who was in it, but you think about what we did then versus what we do now, it's like, but there was a lot of work, a lot of development because of shrinking, more layers, and we see that same movie is going to play out in advanced packaging. And that's why we, as a foundational technology provider, want to be in that. So just a quick commercial on MKS. Last year, $3.6 billion, as you heard, but I want to point out the 2 numbers on the lower part, the 2 middle panels, 85%, 70%. So 85% is the number that describes the number of tools in every semiconductor fab in the world. There's thousands on every chip fab in the world. 85% of them have multiple MKS subsystems in it. 85%. So the big 5 equipment OEMs, ASML was one of them, KLA, right? Inspection, number 1. Applied Lam, Tokyo Electron, the big dep and etch guys, the other market share. All 5 together is 85% of every piece of equipment in every fab in the world today. And we're on every one of their tools. Not just with one thing, with multiple things. We have some strategies called surround the chamber, surround the workpiece. We surround it, right, with multiple things. So then we said, well, that's key. We're foundational to the entire semiconductor equipment industry and therefore the whole industry. But then the other number, 70%, is about how many steps we address in making those advanced packages. No other company even comes close to that. And more importantly, we address not just the equipment to make those 70% of steps. We actually provide the chemistry as well. So we've added a consumables part, which is just as important to that mix. So that's really how we're positioning MKS. This slide's a little busy, but I'll walk you through it. Look at the rows and columns in the middle. You have three groups: vacuum, photonics, materials. Those are three divisions, divided into kind of their markets. A vacuum type of market, think applied lam-tel, surround the chamber, a vacuum chamber. Photonics, think ASML, KLA, everything that has to do with photonics. Think laser systems and lasers. And the motion, as I talked earlier, motion, optics, how do you get the laser beam to the workpiece? How do you measure the laser power? How do you measure the waste of the beam? All that is all the products in the photonics group. And then materials is the Aditech group, which is chemistry plating equipment. So we want to be number 1 or 2 in these. We are number 1 or 2 in most of these categories. Over the top, you see these two bars. One's called surround the wafer, and one's called surround the workpiece. Surround the wafer is, of course, all the etch tools and deposition tools, so that's a vacuum group. But it also has photonics, because surrounding the wafer is a lithography tool and inspection tool. And then optimize the interconnect, or surround the workpiece, but focused on optimizing the interconnect, making that package. That, of course, has the laser systems tools, drilling holes, and, of course, the Aditech tool, cleaning it, putting copper in it, and then the equipment to do that as well. A little bit of, we had to try to explain to investors, like, where are we in that supply chain? We're a little complex, so I don't know if this actually helps, but I'll try. On the left is the semiconductor food chain. On the right is the electronics and packaging food chain. And where we sit at the top, obviously, it's an MKS slide, so we're always at the top, right? But in the semiconductor food chain, we provide these critical subsystems. Our customers are the capital equipment OEMs. I just mentioned the 5. And then they sell to the chip guys. Okay? And the chip guys make the chips. On the right, electronics and packaging, a little more complex. So we make critical subsystems. These are the lasers and motion and optics. They could go to our own capital equipment. So we're actually vertically integrated there. We actually make laser drilling systems and chemical plating systems. And I'll show you some pictures of those next. And then we also added chemistry, as I mentioned before. So who are our customers there? They are the PCB manufacturers and or package substrate manufacturers. Just as an inside, when we were doing the M&A, people kept saying package substrate and PCB, and I said, they kind of look the same. Aren't they the same? Yes, they're all PCBs. So you should know that. The industry said we didn't want to use the word PCB for something interesting and sexy and new, because PCBs have this connotation of, like, why would we want to buy a company in PCBs, right? So let's make a new name. So they did, but it's this PCB. Those companies you're probably not as familiar with. So some of these companies, for instance, Shinko, Unimicron, Ibiden, Samsung, TSMC, even, sorry, not TSMC. These guys are making the substrate, the 20 layers, 40 layers, whatever it is, using our tools, competitors' tools, our chemistry, and our chemistry equipment. There's no chips on it. They just provide this big block of interconnect. That's it. And they provide it to OSATs, who then put the chips on top. So they take the chips from the guys on the left, yeah, and they put those chips onto those interconnects. And then, of course, then they sell, obviously, to the device makers. So Apple, Samsung, those guys. So when you think about the entire electronic supply chain, this is where MKS plays, the broadest supplier of all these technologies. And we're doing it not because we want to be bigger. We're doing it because it's critical, and we want to be in everything that's critical to enabling this. So let's talk about some of the key industry challenges. The three here, maybe they're all the same in every industry: productivity, yield, accuracy. I only have time to talk about the first one, but I will talk about that here because it's relevant also to the photonics group here, and that's laser drilling systems. But we also have chemistry, plating equipment, and precision motion to move chips close to each other and accurately so you can bond them together. Just for scale, the picture at the top is a laser drilling system. Panels go in the right, they get drilled, panels come out in the left. Just for scale, the height is 6 feet, and the length is 9, 10 feet. Okay, so that's the size of that tool. In the middle is a chemistry plating tool. Just for scale, the size is 20 feet high and 100 meters long. Meters, right? So in a factory for plating, you might have 5 of them. So basically, when we have a new greenfield, we're working very closely with the customer because they're building the factory around our tool. It literally is the factory, okay? So that gives you a sense of scale. And so a little more simplified, these are the core building blocks. I think that picture I showed earlier was complex, but simply there's a semiconductor. I've got to package it somehow through wafers, and then the package substrate, remember, just another PCB, and then an even more complex PCB. The whole idea is I've got to get the chip to the outside world. And before, I would just do some wire bonds, and I'm talking to the outside world with a chip. I can't do that anymore because I have multiple chips talking to each other, and I've got to have different layers of interconnection as it fans out. Okay, so that's really as simple as that. And then, of course, we dial down and call that optimized interconnect. So you're drilling holes. You think about this cartoon, a cross-section, especially in the middle, you can see it looks like a semiconductor back-end chip. If some of you have seen semiconductor cross-sections, copper interconnects, different layers, holes connecting them in lines and spaces. It's exactly the same thing on a larger scale today, but shrinking every day and more layers every day. And so when you think about the process flow for that, so these substrates, I think there's a couple of substrate makers here. These are, as I said, polymers with glass fibers, but they also have copper on top. So it's called copper-clad laminate. So there's a layer of copper on top. I got to drill a hole through that copper and through the polymer, and then I can fill it, and I've got some copper on top already. You guys are photonics guys, right? What happens when you shoot a laser at a nice shiny surface? Yeah, bounces back, it doesn't absorb, nothing good happens, right? And so we have to pre-treat it. And how do you pre-treat it? Well, you put a coating, a blackening, in a Atotech wet chemistry bath. Yeah? So it's already using Atotech for that. Then you drill it, so it's got to come out, and then you got to do the drilling. Before we bought Atotech and brought them into the family, they were always saying we should buy a laser company because then we'd have the whole process in one company. They had that missing piece. Now they're all together. So then the laser drills it, and as some of you know, this is not like a nice lathe that's kind of carving out. It is an explosion. You're shooting a laser burst and you blow it up. And so what happens when you blow things up? Yeah, shrapnel, right? Everything goes to the side. You got to clean it. Then you got to pre-treat the surface, and then you want to put the copper in that hole. And electrolytic plating is the fastest. Electrolytic means I use electricity, right? I can only use electricity, though, if there is a continuous conductive surface. And the hole, remember, only the copper's on top. The hole is polymer and glass fibers. There is no continuous conductive surface, so I've got to do electro-less, no electricity, copper plating first. It's slower. I've got to do it right. Can you imagine trying to put a nice layer of metal on a hole you just blew up with glass fibers sticking out? Literally, when you do cross-section, just glass fibers sticking out. But once you do that, then you can do electrolytic, which is much faster, and you have to fill it. And now, here's a challenge. The holes are getting deeper, higher aspect ratio. How do you tell chemistry atoms to go plate the bottom first? Don't plate the sides, because you pinch it off, you got a hole, right? And by the way, don't plate the top, because I don't have to remove as much there. So we are literally using chemistry formulations to plate at the bottom of the hole first and fill it from the bottom up while we're preventing plating on top. So that's why Atotech That division's gross margin is actually the highest in our company. It's higher than the optics we send to ASML, right? It's not an easy thing to do. But we do that. And here's a little picture now focusing on one particular step, the laser drilling. On the lower right is a laser drilling tool, drilling stuff. I'll show you more about that. But on the left is something interesting. And this is where a lot of photonics, and this is a reason why we think about photonics as bigger than just photons. We think about it in motion, think about optical train, how to get it there, as well as the laser. X-axis is how fast, how far I can move, right, with whatever technique I'm going to move the laser. On the vertical axis is how fast I can move that laser and pulse it. So the first type of motion on the lower right is motion stage, yeah? Just motion moving back and forth. So it moves a lot further range, but not as fast. The second motion is galvanometer on top, okay? And that can steer the beam. That is less range, but faster. And then the last one is even less range, but really fast, and it's called an AOD, acousto-optic deflector. And we use all three. So you're probably wondering, what is an acousto-optic deflector? This is where photonics really comes in handy, right? So number one, it's a crystal. There's no moving parts, so high reliability. You put an RF drive on the bottom in the cartoon. You can see the coil on the left in the picture. And that's a megahertz RF frequency. And because you're putting that megahertz frequency, you can actually move and control the beam as it goes through the deflector, the optical crystal. You can move it so it's going this way. You can move it so it's going that way. You can change the amplitude, therefore the power, really at the megahertz regime, okay? So that's the photonics innovation. And here's what happens. On the right is a real laser drilling tool, drilling holes in a real panel. On the left is the cartoon that shows you the laser going through the acousto-optic deflector, the galvanometer, and then the motion moves. So all three motion. And you gotta have the software to control all this, right? Because the holes are not always in the same place. By the way, the holes sometimes are not the same size. And this acousto-optic deflector can actually drill holes of different sizes along the way serially. Most other tools have to drill one size hole, come back, do the whole panel over again, a different size hole. Notice the really interesting number, drilling holes at 15,000 per second. That's not a typo. So I think when we were doing diligence, being a little technical, I said, is that a typo? How do you drill 15,000 holes in 1 second? That's just hard to imagine. And they said, well, John, don't you guys make nanosecond pulse lasers? Huh? I said, yeah. Okay, what's a nanosecond pulse? It's the length of the pulse of that laser. We make that. We also make picosecond, femtosecond, some of you guys do. So nanosecond means the pulse is only a nanosecond in time. So how many pulses can I put in a second? Yeah, a billion, sorry. Yeah, a lot. More than the 15,000. So I got lots of time and space to put a lot of holes, a lot of pulses into it. And I do. But you got to move it, right? You got to move it really fast and coordinate it. And so that is literally how we are using, an example of how we are using photonics and all the things that we think photonics is, motion, optics, and lasers, to enable AI because of packaging. Okay? And so I wanted to stop there because we can talk forever about packaging, but I think for the photonics community, a little different spin for all of you, because I think a lot of you are talking about different other applications. How do we make photonics be the communication mechanism between chips, et cetera? All good, and I hope it happens, right? But here, photonics is already, something critical for making AI chips today. Thank you very much.
Thank you very much. John, I honestly can say that we saved the best presentation for the end.
Yeah, you're always nice.
Because photonics is not only a semiconductor technology. My conclusion is that without photonics, there are no semiconductors.
Yes, and not a lot of other things, by the way, yeah.
Are there any questions for John? I'm coming to you with the microphone. I want to do this because it's an honor for me that you are asking a question to him.
Thank you.
Thank you. A great presentation, by the way. I like the detail and the strategy, the combination, really good. A quick question on your net R&D. It's 8% in 2023. What do you expect? It's a good indicator for you, let's say, how the market is moving. So what will it be in 24, 25, you know?
Yeah, you get that question from investors too, I bet, right? What's your R&D and why is it where it is? Our R&D is actually, percentage of revenue is actually fairly low relative to our peers. And the reason it is because a third of our revenue comes from what we call specialty industrials. And these are just a various bunch of markets where we put not so much R&D into those. We leverage the R&D we put into semiconductor and electronics and packaging. And so an example would be, we make pressure transducers. A lot of you guys have vacuum equipment, right? You probably bought an MKS, Baratron to measure your pressure. Well, we're doing it for semi. You know, but the healthcare company calls us and, you know, we want to do sterilization of surgery equipment in a chamber, and we want to know what the pressure is, and we say, your Baratron's great. Can we buy some? I said, yes. Can you make it blue? He said, no. You buy it as is. It's the range. It's all a spec. Please. And they, you know, it's $4 million a year for 30 years. So we don't even have a sales guy call. It's just like, please use it. So we are able to leverage the R&D a little bit that way. So if you were to take a third of the revenue out, the R&D would be kind of more in line, I guess, with some of the high-tech competitors we have. And that's a strategy, you know, because you get investors saying, why don't you sell those things, right? You know, I said, well, they make good money, and I don't do anything. I don't sell, I don't, you know, I do some, for sure, right? So, and to your point, we don't have an R&D percentage target. I've told investors that any CEO that tells you R&D should always be a percentage of revenue in a cyclical industry, you should run away. That doesn't make any sense, right? R&D has to be stable and over time. And then I came from R&D. And so just like my predecessor came from operations, we kind of can sniff BS, right? He can sniff it from operations folks because he did it. I can sniff it from R&D folks because we did it, you know, at Bell Labs, right? So we are very much a company that says you're not entitled to your R&D. Every year you've got to defend it. And some years we might say, you know what, I need you to sell stuff in this market that I'm not going to put any R&D in for a few years because I need to take your money and move it over here because that's the fastest way we grow the whole company. It's a different job. It's sometimes harder, actually. But as long as we're all in the company together, then I think that's the culture part, too, that I spend a lot of time on. But it's a good question. Yeah.
Got it. Thank you.
Yeah.
John T.C. Lee, thank you so much.
Thank you. Okay. All right.